Alright, in this video I will be talking about the Tschirnhausen transformation, which is a polynomial transformation that eliminates terms. So for example, let's look at a simple general case. For a quadratic, ax squared plus bx plus c is equal to 0, we could eliminate the bx term by setting x is equal to y minus b over 2a, where this will help us eliminate the bx term, giving us y squared minus b squared minus 4ac all over 4a squared is equal to 0. And here we can simply solve for y, as it is just taking the square root, so you get plus or minus the square root of b squared minus 4ac all over 4a squared. This simplifies down to y is equal to plus or minus the square root of b squared minus 4ac all over 2a. And x is just y minus b over 2a, which is a quadratic formula. X is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So we see that this transformation is called a linear transformation. So this is pretty much a linear transformation, and it helps us only eliminate just one term from the equation. And here we could extend this to a cubic polynomial. So for the cubic ax cubed plus bx squared plus cx plus d is equal to 0, we could eliminate the bx squared term by setting x is equal to y minus b over 3a, which in turn gives us a depressed cubic polynomial in the form y cubed plus py plus q is equal to 0, where we again applied a linear transformation. So now what we will do, if we want to just take the cube root, is apply a second transformation. We could have applied it to the general cubic, but we're going to use a depressed cubic as it is much more simpler. Here we would have to make a quadratic transformation. So we have y, or z, is equal to y squared plus my plus n. And here this is where it gets a little bit tricky, because we have several ways of approaching this and making a polynomial in terms of z to solve. So we either have to make a matrix or a determinant, which is called a resultant between two polynomials, and our polynomial is, or our original polynomial has a degree of 3, and our transformation has a degree of 2. And we have to add those degrees, and we get that n by n matrix, which is a 5 by 5 in this case. So we have 1, 0, p, q, 0, and we just shift the 1, 0, p, q to the right, so we get, in the second row, we get 1, 0, p, q. So we have the original polynomial in the first two rows. Now in the third, fourth, and fifth row, we're going to go our transformed polynomial. So we have 1, m, and n minus z is 0, 0. And just move it one to the right. So we have 1, m, n minus z, 0, and 0, 0, 1, m, n minus z. And that is our matrix, and we must find the determinant, because this is a resultant of the polynomial f comma g. So the main goal is to simply use determinant formula to find the determinant of this long expression, which is a long expression, as I will write here. So the long expression we will get is z cubed plus 2p minus 3n z squared. And here we will have the z terms, which are going to be m squared p plus 3mq plus 3n squared minus 4np plus p squared z, and for the constant terms it will just be plus m cubed q minus m squared n p minus 3m n q plus m p q minus n cubed plus 2n squared p minus n p squared and minus q squared, and that is equal to 0. Because if we want to relate the general depressed cubics roots such that it relates to that of the transformed quadratic or the transformation. So pretty much we want our quadratic in terms of y to share a root with the cubic. So pretty much shares root with cubic. So what we want to do is simply eliminate the z squared and z terms. And by doing that, we simply set 2p minus 3n equal to 0, where we solve for n. So we get 2p is equal to 3n, and n is equal to 2p over 3. And now just plugging in that value of n into every other expression, we will get m squared p plus 3mq plus 3 times 4 and p squared over 9 minus 8p squared over 3 plus p squared. We just substituted n equals 2p over 3. So here we have m squared p plus 3mq plus 4p squared over 3 minus 8p squared over 3 plus p squared. We see we have two p squareds, so we could just combine the p squared terms, which will give us negative p squared over 3. Here we have 4 minus 8, that is negative 4, and negative 4 over 3 plus 1, that is negative 1 over 3, so it's negative p squared over 3. So we have m squared p plus 3mq. Now you have to solve for m such that the linear z term becomes 0. So we have 3m squared p plus 9mq minus p squared is equal to 0. So now we simply just have to use a quadratic formula to solve for m. So m is equal to negative 9q plus or minus a square root of 81q squared minus or plus 12p squared. And since it's multiplied by p, it's going to be p cubed instead of squared. And that is all divided by 2 times 3p, which is 6p. So we see here that we just have to plug in m and n into the constant. So we now end up eliminating the two terms z squared and z. So now we have a cubic in terms of z such that we just have to simply have z cubed plus r is equal to 0, where we just take the cube root of r. So z would be the negative cube root of r, where r is simply just all of the constant. So what would we just have to plug in m and n into the constant. So after expanding out the constant, we get that r, which is our constant, is equal to negative 729 q to the 4 plus 81 q cubed times the square root of 81 q squared plus 12 p cubed minus 216 q squared times p cubed plus 12 q p cubed times the square root of 81 q squared plus 12 p cubed minus 16 p to the 6, and that is all divided by 54p cubed. 4p cubed. So now that we have r, we can simply just take the cube root of r and solve for z, and after doing that we see that z is equal to the cube root of, or the negative cube root of r, and n was equal to 2p over 3, and m was equal to negative 9q plus the square root of 81q squared plus 12p cubed divided by 6p. And here we used the positive square root, so it has to be positive because the positive square root gives these specific signs. If we had to use the negative square root, we would have gotten different signs. So here now what we have to do is simply plug in z into that, z in quadratic, and we have to solve using the quadratic problem in terms of y. So y is equal to negative m plus or minus the square root of m squared minus 4n plus 4z all over 2. And now solving for x is simply just negative m plus or minus the square root of m squared minus 4n plus 4z over 2 minus b over 3a. And we know that m, n, and z are all constructed off of p and q. So that is that for the cubic polynomial. And we know that m and n and z will always relate to the transform quadratic. But the thing is, we should keep this in mind, that this quadratic only gives two solutions, but one of the solutions from this quadratic will be a false solution to the depressed cubic, so we have to test which solution is right, because this only gives one. And if you want to find the other solutions, you simply just have to multiply by the root of unity, which is -1 plus or minus I root 3 over 2. And after solving for y with the root of unity, it will give you one of the other solutions to the cubic. So let's go ahead and look at a example. Let's go ahead and look at the cubic x cubed minus 3x plus 2 is equal to 0. So the first thing you want to do is pretty much make the quadratic transformation, which is y is equal to x squared plus mx plus n. We already know n from earlier is 2p over 3. So p is -3, so n is equal to -2. So we have my 2. I need to make a matrix that represents the cubic that we have right now on the top. So the matrix is going to be 1, 0, -3, 2, 0, 0, 1, 0, -3, 2, 1, m, -2 minus y, 0, 0, 0, 1, m, -2 minus y, 0, 0, 0, 1, m, -2 minus y, and that is going to be the matrix that we have. And then find the determinant of this matrix will give us the cubic in terms of y, which is y cubed plus -3m squared plus 6m minus 3, and that's all multiplied by y. And then the constant, -2 plus 6m minus 6m squared plus 2m cubed. So now we just simply have to eliminate the y term by setting -3m squared plus 6m minus 3 equal to 0. Factoring on a -3 divided by -3, we end up getting m squared minus 2m plus 1 is equal to 0, where this is a perfect square in terms of m minus 1 squared, and that is equal to 0, and m is simply equal to 1. So here, we see that we end up getting that this becomes 0, so it vanishes. I have to plug everything into the constant term, but if we notice, the constant is a perfect cube by just factoring out a 2. So we get 2 times m cubed minus 3m squared plus 3m minus 1. This is m minus 1 cubed, and that is multiplied by 2. So plugging in m equals 1 results in this being equal to 0. So the constant also vanishes. So we end up getting that y cubed is equal to 0, whereas y is equal to 0. So we found m and n, so our quadratic is simply 0 is equal to x squared plus x minus 2. Factoring this quadratic, we end up getting that x minus 1 times x plus 2 are our two factors, as we are simply combining two numbers that multiply to -2 and add up to +1. So now we have to simply check which of these satisfy our cubic. So x is equal to 1 and x equals 2. So we're going to plug in both of our solutions to see which one is true. So plugging in 1, we get 1 minus 3 plus 2, and that equals 0. So that is satisfied. Now plugging in 2, end up getting 8 minus 6 plus 2 is equal to 0. So we see that this is a special case where we have our transformed quadratic in terms of our two solutions for the cubic. So here we notice that x equals 1 and x equals 2 is the solution to the cubic above, x is equal to 1, comma 2. But the reason why this happens is mainly because this cubic has a multiplicity, mainly a repeated root. And if we go ahead and look at that, we see that the cubic can be factored out to be x minus 1 squared times x plus 2. So this is the same thing as this. So this cubic is the same thing as this factored cubic. Let's go ahead and look at one more example. So the second cubic we're going to look at is a depressed cubic, which is x cubed minus 6x minus 9 is equal to 0. Using the quadratic transformation, y is equal to x squared plus mx plus, and n is equal to 2p over 3. Here, p is negative 6, so we have 2 times negative 6 over 3, which is equal to negative 4. So, you end up getting minus 4 for n. So here, all we have to do is simply solve for m. And after finding the resultant of our two polynomials, we see that we have our cubic in terms of y. So the cubic we're going to get is simply y cubed plus negative 27m and minus 6m squared minus 12y. And then the constants, which is going to be negative 65 minus 54m minus 24m squared and minus 9m cubed. And that is equal to 0. So here we simply just have to solve for m and eliminate the y term again. So it is going to be 6m squared plus 27m plus 12 is equal to 0. The reason we changed the sign is mainly because we divided by negative 1. So here what we have to do now is simply just go ahead and use the quadratic formula. So we end up getting that m is equal to negative 27 plus or minus the square root of 27 squared, which is 729, minus 4 times 12, which is 48, and times 6, which is 288, so minus 288. And that is all divided by 12. And here we end up getting that 729 minus 488 will become 441. It's 441. And the square root of 441 is the same thing as 21. It's 21. Now we're just going to solve for the positive counterpart of the 21. So it's going to be just negative 27 plus 21, which results in negative 6 over 12, which will give us negative 1/2 for m. And if we do the negative counterpart, we end up getting negative 27 minus 21 over 12, which gives us 48, or negative 48 over 12, which gives us 4. Negative 4. So we're going to choose m is equal to 4, as that is much more easier to work with. So we're going to see if the y term vanishes. So we see we have negative 6 times 16. That is negative 96. And 4 times 27. That is plus 108 minus 12. And negative 96 minus 12, that is 108. And then plus 108. This gives 0 because they cancel each other out. So negative 4 is our preferred solution for m. So we now have m is equal to 4, or negative 4. And now we simply see that our y term will vanish, and we simply have to calculate what is the constant. So we have y cubed plus and negative 65, and negative 4 times negative 54, that is plus 216, and 24 times 16, that is 384, so that's minus 384, because the negative 4 becomes a 16 when squared, and 9 times 64, they're both negative, so it's plus 576. So it is 576 plus 216, that is 792, minus 65 and minus 384. That is 384 minus 65, and that gives 343. So we have that is plus 243. And solving for y, we end up getting that y is equal to negative 7. So we see that we have either negative 7 or negative 7 times negative 1 plus or minus I root 3 over 2. But we're only going to use negative 7. So let's go ahead and plug in everything we know now. So we have negative 7 is equal to x squared minus 4x minus 4. What we are going to go ahead and do is go ahead and complete the squares. So we have to add 8 to both sides. So it is x squared minus 4x plus 4. And that is 1. So we end up getting that we have x minus 2 squared is equal to 1. And taking the square root, we end up getting x minus 2 is equal to plus or minus 1. Solving for x, we end up getting that x is equal to either negative 1 minus plus 2 or 1 plus 2. So x could either be positive 1 or 3. Let's go ahead and verify which one could be a possible solution. Let's test 1 first. We have 1 minus 6 minus 9. And that simply just becomes negative 14, which is not a solution. So x equals 1 is not a solution. Now let's check 3. 3 cubed is 27. And 6 times 3 is 18, so it's minus 18, minus 9. 18 plus 9 gives 27. So here we have 27 minus 27, that equals 0. So x equals 3 is a solution. And you could also get the other two complex solutions using the roots of unity and plugging in y is equal to negative 7 times negative 1 plus or minus I root 3 over 2. So we see that the Tschirnhausen transformation does work and gives us our solutions. And we avoid the whole mess of using the cubic formula, which sure might be slower and faster than the Tschirnhausen method, but we end up having to solve a quadratic in the end. And similarly, we can expand this to the quartic, which is a fourth degree polynomial, which is ax to the 4 plus bx cubed. Then we just continue on going, and after depressing it, we get px squared plus qx plus r is equal to 0. Here we could also apply another quadratic transformation. Y is equal to x squared plus mx plus n. And here, instead of eliminating the x squared term to solve a trinomial, we simply eliminate the qx term, so that we simply solve a quartic in terms of y to the 4 plus u y squared plus v, where u and v are values built off of p, q, and r, which then gives us a solution of y is equal to the square root, or plus or minus the square root of u, or negative u, plus or minus the square root of u squared minus 4v all over 2, which gives us all four solutions. And plugging that in, we simply get that x is equal to negative m plus or minus the square root of m squared minus 4n plus 4 times plus or minus the square root of negative u plus or minus root u squared minus 4v all over 2, and that is also all divided by 2. So we see that after using the Tschirnhausen method for, or Tschirnhausen transformation for the quartic, we are bound to solve a easier quartic, or we just have to solve a quadratic and then solve another quadratic so we could get one of the solutions to the original quartic. So that's pretty much it for this video. So hopefully you learned something new with this, and thanks for watching.